Hi, physics students, and welcome to the last subtopic of topic 5. We spent a lot of time talking about charges, electric fields, electric currents, electric potential difference, and the IB has decided to sneak in this topic of magnetism at the very end of topic 5. Now, if you're in higher level, we will continue to study magnetism and its relation to electrical fields and current in our next higher level core topic. If you're in standard level, this is sort of all you get regarding magnetism, okay? Now, magnetism is in this topic because it's intimately related to electric currents and electric fields, as we will see in just a short while. So just to sort of start off, you've probably all had experiences with magnets, playing with toys as a child with magnets, refrigerator magnets, that sort of thing. The thing about magnets, what makes them so cool is that it seems like it's magical, right? The way that you have two pieces of metal that can either stick together or push each other apart, okay? So we're going to talk about not about how magical they are, although they're really cool and fun to play with, but we're going to talk about the physics behind magnets, okay? Now, I'm just going to barely touch the tip of the iceberg in terms of magnetism. If you go on to study engineering, mathematics, physics, whatever in college, you will study electricity and magnetism in much more detail. So remember, this is as being sort of a survey physics course. We can't spend too much time on this, although you would spend in college an entire year taking electricity and magnetism courses, or E&M courses, as we say, okay? So we'll start off by just defining what a magnet is. A magnet is simply a piece of material around which a magnetic field exists, and we use the term B field for magnetic fields, okay? And it's a vector field, all right? I'm going to talk a little bit about what are called magnetic domains. This is not necessarily part of the IB curriculum, but everyone always asks, what is it that makes a piece of metal magnetic? How does a magnet actually work? So I'm going to just spend a little bit of time talking about something called domains. Something that is magnetic is made up of a material, typically a metal. It's made up of little tiny magnetic masses on the molecular level called domains, and they exist due to the magnetic properties of the motion of electrons in the atom and different shells around the nucleus, okay? In an unmagnetized material, the domains kind of point in all directions. If the material becomes magnetized, and I'll talk about how we do this in the next slide, all the little domains sort of line up parallel to one another. And it turns out that the domains themselves are a bunch of small little magnets. So all the tiny north poles add up to one end and the south poles add up to the other. And the effect is that the whole piece of material has one big north pole at one end and one big south pole on the other. Now, domains also explain that when a magnet is broken into two, how it makes two small magnets. If you want to make a magnet, first of all, you have to take a material that has domains in it, such as a piece of metal, okay? If you expose that metal or touch that metal to a permanent magnet, something that's already magnetized, then what you can do is you can align all those domains in the same direction. And in fact, that piece of metal, which was before not magnetized, becomes temporarily a magnet itself, okay? To destroy magnets, you need to make the domains lie all in random arrangements like it was before it was magnetized, okay? Now we're getting into the super important stuff. Now, B fields, magnetic fields, are only known to exist around two things. Number one, a magnet. Number two, moving electric charges. Okay? We'll be playing around in class with compasses. Turns out that compasses are themselves little tiny magnetic needles that are free to move around in an enclosed, usually circular case. Okay? And you can see how the presence of a bar magnet affects this magnetic needle. Now, all these little bits in space that have the white and the red arrows, those are all themselves little, it's like you had little tiny bar magnets everywhere, and they basically show you the shape of the magnetic field around a bar magnet, okay? Here's a case where we have moving electric charge or current through a coiled wire, and you can see the shape of the magnetic field that results. We'll talk a little bit more about the shapes and the configurations of magnetic field lines, okay? Now, the properties of a magnet, turns out they originate at certain regions in the magnet, which are called poles, okay? Now, in a bar magnet, these are near the ends. And experiments show that there are only two kinds of poles. Now, remember we only had two kinds of charges, positive and negative? Well, we have two kinds of poles, and we call them north and south for want of a better description. And this probably has geographic origins. But anyway, north and south, it turns out that like poles repel each other and unlike poles attract. So here you have two like poles. Okay, you turn this magnet around and they stick together because those are unlike poles. Okay, so like charges, like poles repel and unlike poles attract. Like charges repel and unlike charges attract. Okay? Poles always occur in equal and opposite pairs. There's no such thing as a magnetic monopole, and this is the big difference between electricity and magnetism, right? We could have isolated point charges, positive or negative. We can have a negative charge in space without having a corresponding positive charge, but you can't have an isolated north or south pole in space without the other. Okay? All right, and permanent magnets, they have what are called magnetic dipoles. And what a dipole is it's a magnet that always has a north and south pole. So they're two poles. Okay, so you see that term dipole once in a while. Okay, all right. Now the magnetic field, or the B field, is simply a region where an object experiences a magnetic force. Remember our definitions of electric and gravitational fields. Those were regions where objects experience forces. In the case of gravity, that object had to have mass. In the case of electric fields, that object had to have a charge. Now we're saying it can be any kind of object, but it has to be specific, okay? It can either be a moving electric charge. If the charge is standing still, it doesn't experience a force, okay? Or any other object which either has molecular domains, such as a paperclip, which is not a magnet, or something that is another magnet, which obviously also has domains, okay? Just to give you an idea of the unit, the SI unit of the magnetic field, it's called the Tesla. And 1 Tesla is a really, really, really big magnetic field. To give you an idea, the magnetic field of the Earth at its surface is about 10 to the minus 4 Teslas, okay? Now, the magnetic field is a vector field, just like gravity and the electric field, okay? And the direction of the magnetic field at a point, by definition, is the direction of the force that acts on a north pole there. Remember how we define the electric field in terms of going into negative charge and out of positive charge? And we defined it that way because we said it was the direction of the electric force that would act on a small positive test charge. Okay, so arbitrarily, we've chosen the north pole as being our sort of test pole, if you will. Okay, and by convention, all physicists have decided that we're going to make magnetic field lines go into south poles and out of north poles, okay? So in that sense, you can see that the south pole is kind of like a negative charge and the north pole is kind of like a positive charge. But remember, these are completely arbitrary, okay? And remember, this magnet here, okay, which has a constant magnetic field between the poles, and there's a fringe pattern on the edges, which you might recognize from the electric field between two parallel plates with a potential difference. These are magnetic dipoles. Okay, so a very important slide here. Here's sort of a summary of the analogy between electric fields and magnetic fields. And I have the really important one here in red. And that is, again, that in the case of magnetism, okay, monopoles do not exist. And the two different kinds of poles in magnetism, they have to occur in pairs. You can't have one without the other. In the case of the electric field, like I said, you could have a single positive or negative charge without the other. And this fact, this difference between the two, has incredibly important ramifications in the way the universe is, okay? So here we have the force rule, similar, two types of charge, affects charges caused by, okay, very, very important. You should also know that, two things. A magnet does not feel a force when it's placed in an electric field, and a stationary charge does not feel a force when placed in a magnetic field. And we'll talk a little bit more about quantifying that later. The charge has to be moving in order to feel a magnetic force when it's in a magnetic field, okay? Okay, so a magnet in a magnetic field will naturally orient itself such that the north pole is pulled towards the south pole because unlike poles attract, and the south pole will be pulled towards the north pole, okay? Now, here's your first exposure, I guess, to magnetic field lines, okay? This is the magnetic field around a common bar magnet with a north and south pole, a dipole, okay? So you can see that you have the field lines going out of the north pole into the south pole, and they kind of curl around space. Normally, we would not draw magnetic field lines starting or ending anywhere but the actual poles. So typically you would actually have it coming out of the ends of the magnet. You see how these field lines are coming out of the side? Now that's because generally this entire region is the North Pole and this entire region is the South Pole. But for example, we would never draw a field line, say, going out like that, out of the middle of a magnet. That's just not the case. Remember the case with electric field lines, we always had them starting or ending on charges, similar in this case. Now, if I had a bunch of little compasses around a bar magnet, they would all line up like this. This diagram down here is a picture of iron filings, which are themselves not magnetic, but they have domains. So the iron filings line up in such a way as to trace out the shape of the magnetic field. It's really, really cool. Okay. All right. And remember, the object experiencing the force in the magnetic field can either be a moving electric charge or any other object that has molecular domains. So paper clips, okay, all these paper clips stick to this magnet because they all have little forces that are pulling them, sticking to the magnet. And if I were to remove one of those paper clips, that little paper clip would itself be a temporary magnet, okay? All right. Now, the fields, you need to know the field configuration of other different kinds of magnets. Here's a horseshoe magnet, which is so north and south, right? So you can see how it's kind of a curl, kind of curved in space. A bar magnet, here you go. This is the typical bar magnet. And these little GIFs are made by taking a transparent piece of plastic and scattering iron filings on top and then laying them on top of these magnets. You need to know how the magnetic field between two like poles, you see? So in fact, there's a spot in between these poles where there's actually no magnetic field whatsoever. So these are like the electric field lines between two like charges. You see they curve away from one another. And then finally, with two unlike poles, you have a very strong magnetic field in between them. Again, this looks very similar to the electric field between two unlike charges, okay, positive and a negative, okay? All right, now if you were to take a magnet and suspend it from a string, okay, when no other magnet is near, that freely suspended magnet would align itself such that it would be aligned with the Earth's magnetic field, and it would be approximately parallel to the Earth's north-south axis. And that's the reason. The reason is because the Earth itself behaves like a large permanent magnet. It is a large permanent magnet. But there are two things about it that are kind of funky that you need to know about. Number one, the south pole of that magnet is actually at the north geographic pole. Number two, the actual poles of the magnets don't actually align to the geographic poles. For example, the south pole of the Earth's magnet, the Earth's large permanent dipole magnet, is somewhere in northern Canada. And not only that, over the course of thousands of years, the geographic location of that pole actually changes significantly, okay? Now, if you've ever seen the Aurora Borealis, this is a really beautiful thing that you see. You usually see it in very high latitudes, either the Arctic or the Antarctic. And what happens here is that you have electrons that are normally streaming from the sun. They get trapped in Earth's magnetic field. And what they do is they collide with molecules in the extreme upper atmosphere. And when that happens, they produce photons of various frequencies, or a light of various colors. And this occurs where the B field is the strongest, so it's in the polar regions only. So remember that when you have a magnetic or electric or gravitational field, wherever you have the field lines that are closest together, you have the stronger field. So it follows that the strongest magnetic field is going to be near the poles of any dipole magnet, okay? And one more thing we have to talk about, I have to remind you about the three-dimensionality of vector situations. We're talking about all these fields that actually exist in three-dimensional space, but we need a way to draw them or write them on a two-dimensional sheet of paper or a screen, okay? And remember that the way we depict a vector going into the page is an X, and if it's coming out of the page, it's a dot, okay? So I just want to introduce to you some B fields of some moving charges. In the case of a wire, okay? All right, there's a certain technique that we can use with our right hand to determine in what direction the magnetic field goes around a wire. Remember, every time we have a moving charge, we have a B field. So current is moving charge. So if you align your thumb in the direction of the current, your other fingers will wrap around in the direction of the B field that's created by that moving charge. And we'll find out later that there are two factors that affect how strong that B field is. Number one, the distance from the wire, and number two, the current in the wire, which is probably not surprising. In the case of a ring, you can also use your sort of thumb rule here to determine that the magnetic field is going to be, in this case, going to the left through the ring. Okay, if I were to depict this two-dimensionally, I would actually show the current as being an X because it's going into the plane of the computer here, and then the current's actually coming out of the computer on the bottom. Okay, so that's a great application of the into and out of the page. Okay. In the case of a solenoid, I'll show you guys these in class. A solenoid is a sort of a column of very tightly packed conducting wire. And what's cool about this is that when we pass a current through it, it creates a fairly uniform magnetic field inside the cylinder where all the field lines are essentially parallel to one another.